Now today we are going to do something called the ratio test. The ratio test is better than all the other tests we've had so far in that it doesn't require us to come up with something else to compare to our series. The ratio test works within the series itself. That is, for example, let's say we have a series that all the ANs are not zero. Okay, we don't, if they're, what to do when there's a zero, we just rewrite the series to get rid of it because zeros do nothing, right? So so all the ANs are not zero. Okay, the reason is because we have to do division with the ratio test. We'll define something called rho, where rho is the limit as of AN plus 1 over AN. So let's so here's this letter called rho, and is drawing P, backwards, and so that's equal to limit n approach infinity of AN plus 1 over AN. Notice that in the definition of the ratio test, it doesn't matter if AN is positive or negative because we're going to slap the absolute value on it anyway. So it works either way. So we have that this thing is called the rho, and then and here's the condition. Now, the first one is if rho is between 0 and 1, but less than 1, it can be 0. In that case, then the series converges absolutely, okay? Because the test is done on the absolute value, so it doesn't matter whether there's a negative sign in there or not. That's the first one. And then the second condition, if rho is bigger than 0 or if rho approach infinity, then the series diverges. And those are the two conditions that we know about the ratio test. The third condition, rho equal to 1, got you nowhere. Okay, it does. Rho equals to 1 does nothing. So rho needs to be either less than 1 or bigger than 1. Having said that, let's prove the first part where rho is less than 1. Okay, now we have proved that if rho is less than 1, then converges. The series converges. So let's prove that because the proof is very, very neat. So so I want to talk about it carefully. And first, our series, of course, has it doesn't have zeros. That way we can do the division. All right. And then right now we have a series where rho is less than 1. Then the first argument is there exists an R. Okay, there exists. The backwards E is a shorthand that stands for there exists. So there exists some number R such that R is this really R is between rho and 1. R exists because we just said that rho is less than 1, right? So we can find something in between rho and 1 and stick it in there, and we'll call that thing R. Okay, and then that's step 1. Step 2, we'll figure out epsilon. Now epsilon will be equal to R minus rho, and being that R is bigger than rho, epsilon is bigger than 0. That's second condition. And when you see epsilon, you know where we're going with this. We're going to do the limit proof with epsilon in it. then because this limit is approaching rho, then by the definition, then there exists a number n. Okay, that backwards E means there exists some integer n such that this the limit term, okay, which is an plus 1 over an minus the distance between this thing and the limit is going to be less than epsilon. If there is for n that's for all n, upside down a means for all n is bigger than the n we choose. So for all, that means we can find some certain number big N such that every small n that's bigger than big N, so all infinite one of them is going to satisfy this condition as long as n is big enough. So it's approaching, remember this thing is approaching rho, so that makes sense, right? They're very close. So you allow us epsilon, and it will be inside. Okay, now so far so good. Next, we are going to, therefore, it would rewrite this thing, then and ignore the absolute value sign. Okay, then this thing an plus 1 over an, and it's gonna be less than epsilon plus rho, because all you have to do is get rid of the absolute value sign, which it still works, right? And then put rho on the other side, and we got here. Now, so next, here comes the magic, the magical point. And because of this relationship, we'll write down the first one, okay? So a big N plus 1, the absolute value, is going to be less than R times a big N. All right, now how do we get that? Is this is epsilon plus 1, and that, of course, is equal to R. Okay, so then we have, so that is, being that that's true for all n, so specifically we will we will write it down for this relationship for n itself. Is it for all bigger than or equal to? I need to be careful with that. Yeah, so the equal to also applies. So we'll write down the first line. All right, that's so far so good, right? So because if you plug big N in here, this relationship will be right there. All right, so that's the first one. The second one we're gonna do is then the following one then, an plus 2 is going to be less than, what happens with n plus 2? Well, n plus 2 is by definition an plus 1. Okay, by this, by plugging in the formula, now we'll have n plus 2, so that becomes n plus 1 and still less than R. So we have this one, and but then we're gonna write that down. That is equal, that's less than, plug an plus 1 in here, so we have R squared, an, big N. All right, so now we see that. And then the third line, so as you can see where this is going, so eventually then an plus 3 is less than R to the power 3 an, okay, when you keep applying the same formula, right? And similarly, then an plus 4 is less than R to the power 4 an. When you add all this stuff up, so then let's add stuff up. So all these get added on one side. We get an plus 1, write it down, plus n plus 2, all the way to 4, okay, to an plus 4 is going to be less than, the other side will be R. We'll factor out the R. And we're going to factor out the an, okay, to save space. So then we start with R, then R squared plus R squared, and this keeps going until R4, right? Because, but in general, you see the pattern, which means that the series, this particular series, if we let it go to infinity, okay, it's going to be less than this series if we let R go to R5, 6, etc. The inequality will hold. And what is the, then next thing we're going to do is that, look at this thing. What is that? That's the geometric series. That is the same as, this is the geometric series of sum of an. An is the common factor, and then R to the power k or something, okay, where k can go to infinity from 1. All right. Now, what was R again? Now look back here, remembering what was R. R is something that's less than 1. We defined it that way in the beginning. So this R, being that this R is less than 1, that means this is geometric series. Therefore, it converges. So this thing converges. And then that means this thing also converges. Okay, so this is also convergence series. So this thing from n, big N plus 1, whatever, and to infinity converges. This also converge because of the bounded monotone convergence, etc. Right? So then, yeah. So once this converges, actually that's just the comparison test, right? The comparison test is something about if we are bounded by another series, then bounded series, then it must converge. All right. So then, therefore the original series converges, which is, did I write down the original series? No? Well, doesn't matter. The point is, if the tail end, this series, of course, is part of the original series, only started with some big N. However, any series converges if its tail end, this is the tail end. Any series converges if the tail end converges. Because the first billion of them don't matter, right? Is we only care about the tail. So if the tail converges, then everything converges, because the tail end is what determines the fate of the series. If you add finite amount of stuff in front, it doesn't change the convergence or divergence. It changes its total value, of course, but not the convergence or divergence. All right, and that finished proof of part 1. Next, let's look at part 2. Now, part 2 is almost identical to part 1, except that instead of a less than 1, we pick something that is bigger than 1. And then everything else follows almost identically. And there is 1, and then all these signs reverse to the other side, and then the solution comes out right away. There is one condition in part 2 where it says, what if rho approach infinity? Okay, where what happens if rho is infinity? Well, in that case, we will simply choose let rho in part 2 be some large number m. Okay, big enough so that the inequality here still works, because if being that rho is infinity, then if you pick a big enough number, then the difference will be less than epsilon, and then and then every other proof will follow the same way, except that you might have to flip the inequality sign. But otherwise, the principle is exactly the same. In part 2, being the r eventually r is positive. I mean, r is bigger than 1, then the geometric series diverges, and then by the comparison test, the whole thing diverges. And that's how part 2 makes sense. Now, please do this proof as part of your homework. And that's part 2. And I will write that down in a little bit. It's a very neat proof, okay? And it's good to figure out how to prove this kind of stuff. It's just for the fun of it. And neat proofs are always fun to read, or fun to try to imitate it yourself. Now, the last theory, the last sentence is that if rho equals to 1, it doesn't say anything. Why? Because we can, for example, consider the p series. Okay, the p series, if you take the limit of the p series, and that is the any p series, if you do an plus 1 over an, it will, being that it's the p series, it will end up being 1. Okay, take a look at this. You have np and n plus 1p. The n is only different by 1. And when n becomes a trillion, that really you don't notice the difference. So then the limit will go to 1. And therefore, as we know, p series converges when p is bigger than 1, and diverges when p is less than or equal to 1. So then therefore the ratio test doesn't tell us anything. Okay, if rho is equal to 1. So please do prove this, prove the ratio test, the entire test, as part of your homework. Next, let's look at example 5.23, where there are 3 examples on how to use the ratio test. Even though the ratio test is quite interesting and somewhat lengthy to prove, to use it is a piece of cake, basically. You just do some manipulation and, calculate limits. Okay, so please do 5.23 as part of your homework. Notice that in part B, at least in my book, this version of the book, you notice there are two summation signs in part B. That's because the second summation sign is just part C. They copy and pasted it there by mistake. So just ignore that part, the second summation sign and all the rest of it. That's part C. And do only the front part. That's it. All right, so please do that as part of your homework. And then we'll go to the next page. Yeah, oh, I should also mention that the algebra, when you do this stuff, the algebra can be quite tedious. You see, like, for example, this is how you do part C. I mean, look at how much stuff you have to write down. But even though the algebra might look a bit of a headache, the math is simple. Okay, and if you can't remember how to do exponents or the factorial especially, please look up somewhere in algebra and refresh yourself what the how to work the factorial. So with that, let's go to the root test. The root test is similar to the root test is similar to the ratio test in that we don't have to come up with some other series and then compare. Who knows if it's bigger, smaller, something. The root test only focus on the series itself, so which is very, very nice. So first, let's look at the root test. Okay. So the root test is probably the only test where we don't even care what an is. The ratio test requires the an to be not 0. The other tests require the an to be positive. The root test doesn't care. It can be 0, negative, anything. Why? Because the root test slaps the absolute value on top and doesn't divide by anything either. It just takes the roots. And you can always take the roots of something. And as you can see, it takes the roots all the way to infinity, which is, you think, wow, how are you going to calculate that? Well, it might not be hard to do, but if it works, then the test will apply accordingly, which is the first condition is that if your row end up being row is always going to be bigger than or equal to 0 because of the square root of something. I mean, not square root, cubic root of, it's the root of the absolute value. But the thing is, if you can prove that it's strictly less than 1, then the sequence converge. Okay. Yeah. Then, the series converges. And then if row is bigger than 1, so that is similar to the ratio test, right? If row is, sorry, why did I write down P? You can't write down P, they're not the same thing. All right, now if row, you draw it this way. Okay, if row is bigger than 1, then the series diverge. Or if row goes to infinity, okay? Or you both write it as equal to infinity, which is okay, I guess. Although always remember that infinity is not a number, so you can't equal to it. But, well, anyway, as row goes to infinity, you know that if it goes to infinity, then this diverge. And so on. But for now, we're going to prove, well, we're going to show why this is the case. There is not a vigorous proof for the root test because, well, the root test proof is more the intuitive approach. For example, that what happens is that if this is true, okay, let's say the limit equals to row, that means if you have a big enough n, when you have a giant n that's a billion or something, for large n, then if n is large, let's say large, okay, and then that would mean that a of n is almost what? Oh, row to the power is almost identical to row to the power n, because when they're very, very big, then they're almost equal, so you can shift the power to row. So then what happens then is the sum of the absolute values. So the sum of that is the absolute series or something, whatever. The absolute we're talking about absolute convergence here. The absolute as n goes from 1 to infinity, an, right? Yeah, that will be equal to, that will be roughly approximate, okay, we'll start at n to be accurate. Okay, so we'll start at n. So in other words, we're looking at the tail end of the series. Now the tail end, we will do it like this. That will be a n plus 1, of course. Sorry, why do I say n plus 1 is n? We'll start at n and then get rid of that. Okay, start at n plus n plus 1, a n plus 1, etc. You keep adding. That is almost equal to being that each one equals to that thing. Yeah, I should write down the big N. I don't mean the small n. Yeah, because we said n large, right? So a big N is almost p to the power big N. So then this is almost equal to, you keep adding here, almost equal to rho to the power big N, and each one correspond to that one, rho n plus 1, etc. Okay, you keep adding forever. And so why are we approximating it? Because we're trying to simulate the geometric series. Now it simulates so this is just the geometric series, and the geometric series has a rule where if it's bigger than 1, so think about the geometric series. Let's see. Okay, so compare this thing to the geometric series. Is it geometric series or give me a second. Right, it is the geometric series. So we have the rule that says this is just rho to the power n. Okay, as a geometric series, the rule says that if the rho is less than 1, then it converges, right? That's converge. All right, and then if rho is equal to or bigger than 1, bigger than or equal to 1, then diverges. That's the rule for the geometric series. So then the two are very close together. The two approximate each other, so they will do the same thing. And is that all right? So there proves our ratio test. It's not a rigorous test, you know. We just say, well, it's almost like it, but we'll just accept it because that's what the book did. So we will accept this as a good enough proof. Okay, things are very close. It's also called a hand waving. You know, see, it's obvious enough. So we'll accept that as proof. So the conclusion is that for the root test, if rho is strictly less than 1, it converges. If it's bigger than 1, it diverges. Now, what happens when rho is equal to 1? If it's equal to 1, then we will consider some kind of a p-series. Now, for rho equals to 1, we will use the p-series as an example to demonstrate that it doesn't do anything. Okay, it can diverge or converge. So the test doesn't work for anything where your limit rho end up being 1. So then you gotta think of something else, if anything, to fix this. So to show that, let's write down the p-series. Now, right now, I'm gonna call the p-series the q-series, okay? Because p and rho look similar, you know. So let's call it something else. So let's consider the series as demonstration. Let's consider the p-series, which I will write it as q. Replace p with q. What am I doing? Okay, and q. Okay, and then this is from n goes from 1 to infinity. That's our p-series. That's renamed q for the moment, just for this case. So then the rho, by definition, this thing here, okay, equals to the limit of n goes to infinity, and then the square root of the p-series, which is 1 over, in our case, we call it q, okay? And the q, and then this is the power n, which will be, when you do the algebra, that equals to, is just, the fraction becomes 1 over n, q minus, yeah, is q over n. Right. See? then because of the cubic root, so the root becomes the division, so that there it is. And then the limit, we still have limit as n goes to infinity. Now what happens to this limit? Well, that limit is so now let's calculate the limit. Okay, so the way we do it is let y equals to what's inside 1 over n to the power q over n, which is just the whole thing. Okay, 1 over n to the power q over n. And then so we take the natural log of y equals to q over n times natural log of 1 over n. That is that right? Which end up being here's q here, and then there's natural log of 1 over natural log. There's no dot there. We're just doing logarithm now. Natural log of 1 over n divided by n, and there's a q in front. Q is just a number. Now at that point we have the infinity over infinity situation, right? In fact, we've done this many times, but we'll do it again. So then that equals to q, and then taking the derivative of natural log is 1 over n. Okay, and then derivative of 1 over n is 1 over n squared minus n squared, and then the derivative of n is just 1, so that all approaches to as n goes to infinity, this all approach 0. Okay, so natural log of y approach 0, which means y approach 1. Well, yeah, that's where natural log is 0. Is natural log of 1 is 0. So then we get and therefore rho equals to 1. Equals to 1. That's rho. That doesn't look like it, does it? Let's write it better. So rho equals to 1. And if it equals to 1, as you can see, then the p-series converges if p is bigger than 1 and diverges if p is smaller than 1 or equal to 1, right? So then rho equal to 1 gives no information, as we claimed earlier. All right, so that's that. That's the demonstration of the root test, halfway proof. Now that we know the root test, let's do the example of a root test. That's example 5.24, where you apply the root test. So that is again just some kind of a limit manipulation. So please do the 5.14 as part of your homework. Sorry, 5.24. Now, as you can see in example 5.24, you have these two series. They both have stuff to the nth root. So if you're going to take nth power. So if you take stuff to the nth root, things are going to work out very nicely for you. Okay, short and quick. So please do that as part of your homework. And then let's go to the next page. Now, how do you use... So far we have come to the end of the chapter, and we have learned various ways of testing convergence. So the book have a list for you, so sort of a strategy as to what test should you take. Some kind of a general idea, which I don't think it really matters that much, but please read through the problem solving strategy on the following page, all the stuff, and then but basically when you look at a problem, you just see what comes to you the best. Okay, and also it's important if you come up with some kind of a chart. I have drawn up the chart, but I will show it to you in the next video when I'll assign homework. So is in other words, I want please draw up a chart that summarizes all the tests. Because the reason you want a chart is because each test has often has really precise requirements, such as p has to be strictly less than 1, or I mean, this is rho has to be strictly less than 1, p has to be bigger than 1, and so on, and an has to be bigger than 0, or bn's bigger. I mean, some of the conditions are confused, like repetitive and yet different, so it's easy to miss the conditions. So if you put all the tests on one page and then summarize it, you don't have to write down every single word. then the whole story will come out much better in doing this section. Let's see. So with that, please do example 5.25, which shows you how to choose different convergence tests. But in reality, you just pick one that looks the best for you and then and hit it. And if it doesn't work, then you have to look at your list of tests and see if something else might work better. So please do example 5.25. Well, the book does even provide a chart of various things on page 517, but I think you should come up with your own chart. Well, maybe based on this chart or based on the where the tests were covered, and because I think the book's chart has too many words in it. Okay, you need a chart that's extremely succinct so you can see it and know exactly what each test takes and fit it all into one page if you can help it. So yeah, I'm a firm believer that your own chart is better. And then in the next video, I will assign homework, and then we will talk about it. There will be quite a bit of homework in this chapter, this section, because it's mostly is not just the ratio and the root test, but sort of let's also summarize everything we've learned and use all the tests available to hit some kind of a series that we don't know how to do. Okay,